Namaskar, my dear friends. Let us see how we can design and simulate active low pass filter first order. So we are going to design a circuit which will give us the cutoff frequency of desired, like cutoff frequency. So we'll do is we have a resistor and capacitor that is going to set the input cutoff, input cutoff frequency for the low pass filter, and this is my input signal of desired or required, like a frequency. Our aim is to understand what is the output or the Bode plot of this particular low pass filter. So as you can see, the, this particular low pass filter is designed for 10 kilohertz. Okay. So at 10 kilohertz, we have minus 3 dB. That is your cutoff frequency, which is there at this particular cursor. Okay. And you can see the input and output signal as well. So probe 2 was actually input signal. So you can see we have 1 kilohertz signal, green color, and red color is PR1, that is probe 1 here, that we have taken here. So why don't we do one thing? We'll open Multisim and we'll design this circuit from scratch. Okay. If you want, you can pause the video and see by yourself how to design it, or otherwise we'll start from scratch. Okay. So let me take a new window. Let me take a new window. And very first thing that you have to do is you have to place the components that is required. Okay, so go to place components. Let us say we need resistors, right? So we'll put resistors. One resistor is here. Let us say at output also we want to put it, like RC damping. Okay, then we need capacitors. So in basic itself, okay, group is basic. Okay, basic, and then we are going to take capacitors. So go to capacitors and put it. If I want, I can rotate it by pressing Ctrl R, and similar to that I'll press Ctrl R to rotate here. So capacitors is fine. Now we need input source. Okay, so go to groups, sources, signal sources. We'll take AC source. Okay, so by default AC source it will be coming for 1 kilohertz 1 volt peak. Then we need power sources as ground, so I'll take ground as well. Okay, so we'll take ground here, and then ground here, and the ground at output. Then we need more power sources for op-amp biasing as well, so I'll take VCC and VEE. So I'll take one VCC and I'll take one VEE. Okay, so these two sources I have taken. The last element that is remaining is my op-amp. So go to groups, come to analog, we have op-amps. You can type your required number, or otherwise select any, that is fine. But what I'm going to do is I'm going to take OPA 2209. Okay, so this is the op-amp that I'm using. So I will take first pair. So first pair I have taken. I will skip it. So second pair is not needed for me. So I'm not going to take. That's all. So this was all about the, like bringing up all the elements. And now quickly I will wire up. So what you have to do is you have to go to the tip of the pin, and the sign changes. You can keep on wiring very nicely. So I'll just put it little up. Okay. So you can quickly wire it up. Then what we are going to do is we are going to have unity gain. Okay, so I will not set any gain right now. I'll not set any gain right now. So I'll just keep it as it is. So I'll keep it in buffer mode. So this is how you design the circuit, almost complete. Okay, now let us do the thing that is needed. What we have to do is we have to change the values of capacitors and like a resistor based on the desired cutoff frequency. So I am going to design for 10 kilo ohm 10 kilohertz cutoff frequency. So for that, let us run first and see what is happening. Okay, so nothing is happening. Let me put a voltage probe here and then run it. So voltage is changing here. First thing that you need to do is you need to go to simulate, and to get Bode plot, go to analyze and simulation, AC sweep, and change your stop frequency to, let us say I'm going to put it 10 megahertz. I don't need very high values, and make it vertical scale as decibel, and then run it. then you are seeing some graph, okay, which is of this thing. Okay, so I'll just make it little bit thicker. So you can see it is oscillating, or it is like giving a cutoff frequency of some value. Let us say -3 dB. If you see, so it is going to give you around 103 hertz, that is 100 hertz. Okay, so 1 kilo ohm and 1 microfarad value gives you 100 hertz. If you want, you can calculate quickly. 1 kilo ohm, right? So 1 kilo ohm is this, and 1 microfarad, so 1 microfarad is this, so it is going to give you 159 hertz. Okay, let me just check once. 1 kilo ohm and 1 microfarad, so 1 kilo ohm and 1 microfarad is giving me 159 hertz. So 159 hertz would be the cutoff frequency. Let me run and show to you again. So it is going to give me -3 dB as around, yeah, it is giving you around 100, it will give you 159 and there is something that is missing here. No problem, no problem. But our aim is to design for 10 kilo ohm. Okay, so for 10 kilohertz. So what you can do, you can change this value to 1.59 kilo ohm or 1.6 kilo ohm. Okay, and this one to 10 nanofarad that was calculated for us. Okay, if you can see the Excel sheet, let us say we want 10 kilo ohm. So for that we have calculated 1.59 kilo ohm, that is 1591 ohms, and 0.01 microfarad, that is 10 nanofarad. Okay, the output is damped a lot, so I'll just put it 100, and this one I'll put it 0.1, very nominal value or very practical value that we always use. And now you run it. So what you are going to see is the cutoff frequency will shift to 10 dB, right? The cutoff frequency will shift to 10 dB. So 10 kilohertz. So you can see here, I am going to set it to 3. So it is going to go to 7 kilohertz. There is something that is happening here. Let me see. Yes, so what was happening is actually this particular capacitor was too high, zero point 0.1 microfarad was too much. Okay, so we should reduce this value so that you can have a proper 3 dB 3 dB at 10 kilohertz. Okay, if you want, you can reduce it more, let us say 1 nanofarad, and then it will give you exactly almost 10 kilohertz. Okay, so you can see, come to -3 dB. Yeah, 3 dB is almost giving you 10 kilohertz. So this is how you debug the circuit and make your desired output. All right, so let me change quickly some other values. Let us say if I want to like have 1000 ohm and zero point 0.1 microfarad, then you are going to get 1.59 kilohertz. So you are going to get 1.59 kilohertz with 100 nanofarad. So I will be getting 100 nanofarad. This is going to be 1.59 kilohertz as cutoff frequency. So let me run it. So you can see you just bring out at 3 dB. So this is 3 point, yeah. So you can see it is 1 kilohertz exactly. Understood? So to design 1 kilohertz, you can very nicely put your calculated value, which was like 0.01 microfarad and 1.59 kilo ohm. Okay. Understood? Now let us say if you want to see the output, what will you do? Since it is 1 kilohertz, it is not a good idea. I am going to keep it 10 kilohertz itself. So for 10 kilohertz, what was the value? 1.59 kilo ohm and 10 nanofarad. Okay, so 1.59 kilo ohm and 10 nanofarad, not 100 nanofarad, 10 nanofarad. So it will shift to 10, I mean 10 kilohertz. So let us run it. So it has shifted to 10 kilohertz. Yeah, it has shifted to 10 kilohertz, my cutoff frequency. Now the input frequency is like 1 kilohertz. So the output we can see very nicely. Let us go to simulate. analyze and simulate, go to transients, and I'll run it for, let us say this is 1 kilohertz signal, so I'll run it for 5 millisecond, that is 5 pulses we want. Okay, so you can see output is very nicely appearing, plus 1 volt, minus 1 volt. If you want, you can increase the thickness of this particular trace so that you can very nicely see. If you want to observe your input signal also, put a voltage probe at the input. Okay, and then rerun it. So your input signal will come in, let us say green color it is coming. Okay, probe 2, that is also plus minus 1 peak to peak. Okay, so if you want, you can change that trace also. So how to make that? I'll just enable that only so that I can keep my trace width little higher. Understood? Now to observe the output attenuation, see it is very nicely appearing. Now my cutoff frequency was 10 kilohertz. So I'll keep input frequency itself more than that. Let us say 15 kilohertz. Okay, and if I run it, my output will not appear at all. Okay, so let us run it. Let us run it. So you can see the red signal is not appearing since it is running for longer time. That's the reason it is doing like this. So I'll run it for little lesser time. Okay, so let us say 1 millisecond I'll run. So you can see output is attenuated. The red signal is attenuated. Understood? So to have a better idea or to have a better picture, you have must design your RC filter in, your active filter in such a fashion that cutoff frequency is more than the input signal frequency. So it will be allowing up to around, let us say 5 kilohertz or something like that. So it's better to feed 1 kilohertz signal only, and you will have your output nicely. You can see output and input are following each other. So thank you guys.